if you growing them, then that's how many permutations do we have here? How many trajectories can we actually construct between the two point out of size 6? Then you probably all know the answer. This is factorial. So it's here in this case it's 720. So of course 720 doesn't sound like a lot, but yeah, we get to n is equal to 1000. We won't be able to enumerate all of these permutations, and so we need to ideally find a way to optimize over the second permutation and find maybe a good objective. So we will need to provide some data or some more information to resolve this input problem. So the one thing that we use in optimal transport a lot, this is why it's actually very much geometric kind of method, is we are going to assume some kind of cost structure on the observation. This could be a distance, this could be a square, this could be the remaining distance. Every time you change this cost or this distance, you enter a new area of here. So for now, let's just simply say this is just a cost. And actually, for every pair of source and target points, we can output a number. And there are also generalizations to quantum, you might output the quantum. But now let's say you get the number. And you will basically need to provide that number for absolutely all of the inputs and targets there. Here we have 6 points left, 6 points right. This means 36. So now, once you have this picture, it takes that much cost to go from this one to this one, and maybe it will be cheaper to go from this to this one. You can formulate the one CS, the computer science 101, most simple problem, which is this optimal assignment, also called linear assignment, or optimal matching problem, where we will very simply say, among all of those 720 permutations, 720 sections, how do we pick that which on average occurs the smallest cost? So on average would be just the and which sort of cost to go from xi to y sigma. So here I would mention variable which for each I, which sigma I form a group. And this problem comes very easy. This is what we tried, has been solved for over. By the way, I just want to clarify if there's any question, feel free to interrupt me anytime. I will be happier. Okay. So this problem is solved in a way. We know how to get this optimization. And this was basically highlighted by Cuturi in the 60s, right around the time the linear programming was taken off. And he called the algorithm the Hungarian algorithm because two Hungarian mathematicians earlier in the century had basically come up with seeds. And then the Hungarian algorithm it's a very combinatorial algorithm. You can imagine here the space for which we're optimizing on is a set of permutations. So one of the engines this, so this Hungarian algorithm has been used a lot in let's say from the 50s to the 70s, 80s. And what you see immediately now in 2020s is that although this is very nice mathematically speaking, it doesn't really scale. The second problem, which I think is the most important, and we will see also a lot of the talk, is that this doesn't accept our stuff. So really, this is like a blueprint of original optimal transport, but it already holds a lot of limitations that we're going to try to find. So what do I mean by it doesn't extend out of sample? Well, imagine this set of random particles are your system, you're observing it, and you're trying to make sense of it. Gas particles in the configuration before and after. I'll provide more examples later. Well, out of this optimization and the recovery of some computation, it's very hard to infer what might happen with a new problem. Of course, you can start thinking about naive near single rule, something like, okay, to this point, you have to find this one, maybe you go up in the same direction, and then you add some super segments or something. So there are a few hacks that you can think of, but it doesn't really work. So I would like you to keep in mind with this overarching goal of trying to compare data that is not fair to the. But this model of communication is not going to work for reasons, and every time we're going to extend it or change it, we are going basically to branch different areas of the work. So as I mentioned, this is very slow. I didn't say why, but roughly the worst case complexity of Hungarian model is the Bureau of entry. So compared to n factorial, of course, Q is tiny, but in Q is way too large for most large scale applications that we have in the. The other reason why the Hungarian approach might be a bit tricky to play with is because it's inherently a combinatorial approach. It's very unstable. So I think it's hard to illustrate this. So here I plotted the function out x and y, right? And I have drawn the links that connect the best matching points. So here the cost, by the way, is square root of the what I will now show you is what happens to this matching when I start moving the particle. Here I'm just moving for simplicity the blue particle. And of course, the physics there, for most of the time, the mechanics stays stable, the optimal permutation stays stable. But then sometimes it just breaks, it jumps, it decides that the permutation goes over that one. And if you just add a indivisible change to the location x, boom, you have a different permutation. So, of course, this is not really a bug, this is the way the code works. But what we will see in the local mechanism is that this is very costly, but also this is very unstable. Usually, in machine learning nowadays, we like everything differentiable. We like to take gradients to compare it. And in a way, if you look at this, optimal matching, the way it changes is very different. So, because I only have 1 hour, I'm not going to spend too much time on this, but this is more or less so, because we have been working a lot in recent years on finding better, more efficient solvers here and the world. And I will talk about one in particular, which is something called the synchron. So this is the big rough to see this idea directly. But basically, think of the synchron algorithm as something that tries to solve the same problem. Permutations, permutation matrices, but with so many some regularizer that helps you go faster and get a solution that is a bit more fractional, a bit more continuous. So let me just try to give an intuition of what the algorithm is more as, by the way, it's but actually so here, as I mentioned, if you solve an optimal problem, you find this kind of assignment, which tells you that this starting point here is entirely connected to it. This is usually represented using the permutation 3, 4, 5, 7, 8, 8, but you can also represent this as permutation. So you will find that, for instance, the first point here is the 2-point cloud, goes connected to the third. The second here goes with the third. Second, the third here goes to the second. So this is the representation of the bijections using a matrix. What the synchron algorithm does is that it adds a regularization here that says, well, this matrix, I would like it to have more blur. I would like it to be more important. And if you do that, here, if you start adding some gamma weights to this regularization, you essentially start seeing a few very thin lines here in the code here as you start increasing regularization. So, in other words, the canonical problem in optimal transport is this idea of a bijection. In practice, when we work with algorithms at market scale, it's more convenient to essentially go to a more continuous perspective and not stay anymore at one point entirely monopolized by another, but then they start doing what people call mass. Here, the more I would increase this value of gamma, the more I would tend it to something that is quite the opposite, which is very much the. So again, I won't have the time to talk too much about the single algorithm. I just want you to keep in mind that from here, which is this Hungarian algorithm, we can move to something that is quadratic or even faster using some regularization. And essentially, what we get is, instead of this permutation, get something that is really a bit softer with a really small fraction of it.
From the 2 point clouds, is the points the same?
Yeah, so that's a good question. So we're going to do my next. I'm trying to do my best to pack a lot of content in a few slides, and so this, I think, was the way to introduce the algorithm. You're perfectly right. The good thing about the single algorithm is that it also helps, and more generally, the coverage formulation, it also helps to handle point clouds that have different sizes. That was another big limitation that again I got. So the other problem that was just now mentioned is what happens if you give it 2 point clouds. So it turns out that Hungarian breaks with bijections. You could look for a subset of the bijections that biject the n-1 to n-1 point, even though the source or target are given. And that actually is very, very costly. The other extension is indeed when you start considering that maybe your data is weighted, weighted observation. To sample or maybe construct those data sets, some of the points we have given. The other extension that people see a lot is mentioned is extensions of optimal transfer where it's no longer that easy to compare the points because they do live in the same space, but you're still trying to do a matching. So a very simple case, imagine you have a 3D scan of someone, and you have a 2D picture of someone, and the person is the same, of course. Even though it sounds a bit far-fetched, you might want to map so associate the point in the 2D picture, this part of the measure, from the picture with this part of the measure. So there are a lot of situations, science or machine learning, where we compare points that do not live in the same place, but where we have the idea that actually they might be associated. So this is the typical scenario where we have to find an association between points in the so I was telling you, how to generalize. So this is an important, crucial problem. It's one that is very much scientific. And here, essentially, what we are going to also see is a link to statistics in the sense that stochastic gradient itself, in the sense that we're gradually no longer going to be assuming that you give me a full data set of points, but more like that all of those points they come from an underlying distribution, and we are receiving those points for our sample, and we can ideally get a very, very large number of samples. We have to so we have and the one thing I want to say is that a lot of the generative tasks that we see so far in learning can most of the time be interpreted as trying to basically push either noise with GANs, 10 years ago, where they were using basically noise in low dimensions to map it to higher dimensions, or now more things that you hear about, these fusions, so matching, which also adopted this model of gradually moving points from one location to another. Finally, I'm not going to talk about this at all, but there are a lot of stochastic extensions where instead of trying to follow the notion of moving from one point to another, you're going to follow stochastic paths. There's also other many other sections of this. So one of the most obvious is here I have presented everything where I have an input measure, the target measure, but it should come with yet another measure. Not 2, but 3 or 4 or 5. The therefore, this multi-marginal optimal. This is another problem where we try to register or connect with multiple coding solutions together, rather than having just one. So, again, this is one of our tutorial slides. Not, I should not do see all of this, but know that essentially optimal transport is a very big field, and it has time, a lot of word jargon. So let me just go very briefly to some of them. So I would say the original model is really can be really found, this idea of matching point clouds of maybe varying size, varying weights. And this is usually called the Cuturi solver, and it has a lot of groups in that memory. And you will see also keywords such as last time distance or current movement distance or ratio distance. When we start moving away from this setting where the points are in the same space, and we start considering points in different places, then this is typically called global factor. If you read here, that's the quadratic assignment of the source, not really defined, just this word. And there are a lot of links here. This is the country. There's a lot of links between global factor and the global finding finding a way to map the graph and source to another graph. And then when we start moving to the more continuous game to having distributions, then this is more the area of, I would say, time map. And there have been a lot of very potential results in the pure mathematics. There were two things that one of the points of identity and capacity. And if you now even start adding stochasticity or a dynamic formulation, then you go to other keywords such as Benoît or Jean-Pierre. I will be covering some of them, but again, I was insisting I'm not able to do it. So all of this looks cool. I would like to present briefly one application which I think is very interesting pricing, which is how optimal transport has appeared as a valuable tool for single-cell genomics. So what is single-cell genomics? I mean, it's how you use this tool for single-cell genomics. What is typically used today to understand the dynamics of your cell when they are given some treatment, perturbation. So let me, I'm not going to do any biology here, but I'm just going to explain a bit the problem. Imagine you have a patient that is sick, maybe with cancer. You're able to extract the 10,000 cells from a biopsy from that patient. What single-cell technology allows us to do is to look at each of those cells, split it open, and count something. We just count, let's say, RNA, pick up other things, and we just see roughly what is going on in that cell at the moment we split it. So this gives us a very high level, but very detailed picture of the activity of the cell. And so typically the dimension here would be very high, because if you are counting the RNA for each of the 25,000 genes that we have in our DNA, this means that you have a histogram of size 25,000 for each cell. So it's a very high dimensional presentation. One of the great things is that this is really detailed. One of the bad things is that to take that measurement, you need to kill yourself. This is a bit on switch. This is a situation where whenever we look at those cells here, we are not really able to put them back to cells. They have more than disappeared. And so what people do is that they take this as your control measure of what's going on in those cells. You sample enough of them so that statistically this is meaningful. And then you let the treatment go forward. Then I take another sample. It might be a bigger one. Here, I think it's similar. This might, it's basically going to be another sample, but now it's going to be representative of the cells after treatment. And now the goal of this, according to the biggest challenge is to be able to make sense of those two programs. And to make sense of this, what we essentially want is to be able to predict from this data what would happen to any cell if it was given this treatment, and hopefully, those are treatments that kill a lot of cells with cancer treatment. Hopefully, you're able to find that the treatment is really tapped to cells. That's what it's mostly killing the other. So it's basically pushing the cells in this healthy area, not too much. And it's really moving them a lot in the area where maybe they are. So this is an important challenge. And so if you are able now to come up with a map that explains per cell the effect of the treatment, the good news is that we can do this for thousands of treatments. And the bad news is that next time the patient comes and gives me, I get the patient cell, I can in silico predict what the treatment could be, but what any of the 1,000 treatments might be doing on that patient's cell, and choose them. I won't have to do this follow again before and after, etc. I'm just going to eavesdrop what happens to the cells of this patient if it was given this treatment, and then think of it. So of course, we're still far from having this working very well, but there's been a lot of progress in this area. So there's one paper that we want that is trying to summarize those how to use optimal transfer in that case. And then we had a paper also earlier in January that is more, it's a bit less concerned with the idea of mapping IEC here, but more about using very large optimal transfer method at scale that use a lot of the flavors of this. Let's compare cells into different spaces. So this is one motivation, one application that is quite interesting, and the other one that you are all familiar with, is sequence generation. So I think what distinguishes those two applications, so sequence and generation. So generation is you just sample noise, you make it appear or look like an image in a way or this might be to GAN, like one set generation, or this could be to neural heat, the diffusion, the plasticity. All of the flavors of this work. But the biggest difference between those two applications, and I just want to highlight that, is that in science, very often we are moving from a complicated to another complicated. We're trying to learn maths, transfer, between one data set A before perturbation and data set B after. In generated, those models, generative AI, I don't want to say generative AI, but in generation, we always start from something that is very simple, typically a Gaussian loss, then we get to something very simple. So, so I will start a bit with the math for now. Any questions you have? So, the first, the simplest tool for optimal transform, one that historically was proposed in the 18th century, is the notion of Morpha. So it's very simply the extension of limitations to something pretty. So when you Morpha, imagine that you have a red quantity distribution with high density, the blue density, and you are going to find a map that will take any point in the red network X, and you will tell me where it has to go in the blue magnitude here. So you will do this repeatedly for all points in the support. And here the biggest requirement is that this works. By this works, I just simply mean that this map here, T, does the job. If you look at it in detail, push forward the red value. So pushing forward means The following thing mathematically means that if you take any subset in the target area, U, let's take this B here, and you look at all the points that landed in the boundary area using T, is T minus 1 inverse set of this set U, you get another set which is going to be in the red line here. And the idea is very simply that we have the same error. Vector of the target here. So according to the target U, U of V is the same as the vector of the starting vector U. So if this sounds complicated for work, it doesn't matter. The only thing that you need to understand is that this red bar here, this key, really everything. Usually there's many of them maps. What more said is this giving. This is the same layer, we find the same layer that we have earlier, same thing of the assignment. This gives me that which does the job, which does the job of pushing all of the points meant to do. But in addition to this, I would like you to give me that which, on average, will incur the least error. The cost of going from X to the source of P of X is. And I am going to integrate this with the source measure. This should be the right to find you a very much slide where we essentially here, this is the continuous distribution projection point. Let me again make a bit brief. There's a few very nice results, not new in the sense that they are from 100 years ago. But if you look at the history of this component, it's kind of fascinating that nothing happened between 1781, or more, in search paper, and Grenier, who proved this result here shortly after in 1987. So the result by Grenier, that thinking because I think it's a beautiful result, it says in optimal transport, if you're comparing two point distributions that have some ice, just have this, something measure happens. If you set the cost to be the square Euclidean distance, which is going to be 99% of our life, then the optimal transport function, the optimal transport map T, this more map that more worried about or thinking about, has got to be G by the gradient of the convex potential. So what do I mean by this? If the function phi is a function from R to R, the gradient of phi is a function which is a vector associated with it. If you the slope of phi at so indeed this path, gradient of phi is a vector vector. It turns out that this map here that we're looking for always needs to be the gradient of even those ones that are here on the page, they will be the optimal transport which we achieve by gradient of common. So this is called the one here. So here I just read, this multifaceted object. I started by telling you about this more the problem of finding the optimal map that takes you from the measure. It turns out that this is historically correct, but nothing would have happened without the insights of Cuturi, who actually got the Nobel Prize in economics 30 years later in the 70s with Kupas, where he actually started looking at optimal transport forms, not so much with the lens of finding an optimal map, but directly as the problem of finding copy. So if you remember my slide in the C4, essentially the big thing that Cuturi did was move away from this idea of bijection, more like a matrix, so a copying matrix. And then he extended this to just a C4. And at the same time, what he did then we show another facet of the cube, and this is called the Cuturi dual problem, which is just simply the dual problem that corresponds to this problem. So I understand this is not to follow this very simple those equations here, but this is basically a linear program which can be seen as a relaxation of this problem, and this is the dual of this problem. So this is historically the main focus of the, and the good thing, and again, this is a quick overview. It turns out that magically those two things kind of go together. This is the top, the linear problem is the dual, the dual here. But it also is the case that you can actually get back this optimal value here from the solutions of those, either of those two, mostly from this thing. And again, this is just the way I'm trying to give you a feel of this area. It turns out, thanks to Grenier, that we can actually recover the optimal motion, the one that takes mass, using the formula that is kind of complicated here, but it simplifies the concept, which is usually called the Gamble-Maclin formula. And so what is this formula? Let me just try to first review. So remember, the most problem is concerned with mapping. Finding the right map. The Cuturi problem above is about finding the joint conflict institutions, and the dual Cuturi problem here at the bottom is a bit simpler. It has a bit of a flavor of what you have seen in metrics, max, mean, discrepancy, and things like that. It just says, okay, give me two probability distributions mu and u. I will try to find two test functions that take a vector in and output a number. And I will try to maximize this problem. So usually this is, if you're familiar with duality, typically this is the question of allocation here, and this is the question of pricing. So you try to find two price functions for those two distributions. And you optimize them with the constraint that the price of f of x, the price of x, f of x, plus the price of y, g of y is similar to the well, I acknowledge this is not the thing, but what those folks here show is that the very high problem of fulfilling this optimal transform map can be solved if you first spend some time solving this linear program. Program is something that you know how to do. Maybe not 20 years. Program, you can actually try to approximate. So this is why I put this little part here. We have actually ways to approximate this. And so once you find this potential here, what you have is a function from R to R. You take the gradient of that function, from either of the functions, you take the gradient of f star, we get a function from R to R. And this operator here is a operator gets very geometric. This is called the twist operator. This is something that the integer basic, where you can basically evaluate the cost. Here x is given, right? You're trying to find where the mass of x goes. You are going to simply take the cost function from x to any point, compute the gradient with respect to x, and see as a map that associates a vector to another vector, and invert it. So if this is the vertical, this is called the twist condition. And you apply this inverse to a vector to vector to another vector, and you get it. And this was too fast. Please, there's lots of references trying to explain basically how to essentially go from this dual problem to the problem and to this most problem. But this is not what I'm going to talk much about today. I'm going to, this is the story I will really want to give you later. I am going to talk now about yet another. It has a lot of ways of extending it. And this is called the dynamic formulation of the transform. This is what you might be familiar with. through, if you've been studying, let's say, flow matching or diffusion. So, what have these formulations here in common? Well, the thing is that they just assume that they work by simply looking at the starting configuration, end configuration. They just try to learn the way to start from the end to one. So here it might be a bit more solid in the linear programs. Those two things here, those three things here are usually called standard outcomes. Because again, the goal is I'm not going to care too much about what happens to you. The only thing I want to learn is negotiation. But it turns out that you can come up with a dynamic formulation of movement. This is usually more demonstrated, less flexible. But it's one where instead of trying to parameterize the problem either as a map, either as a topic or as a dual set of dual functions, we will parameterize it as a velocity field and an interpolation. So this is usually called the Benamo-Brunier formulation, and let me try to explain a bit more the idea. So they say, okay, a lot of times we have this two quality distribution, two examples here, and instead of trying to draw directly the arrows of solved target, let's try to have a more dynamic, microscopic view of what. So this is going to, in a way, answer more carefully very early puzzle than I would do. So in the early puzzle, I suppose they said who went where. Now it's going to be actually how did they go? How did they go from source to target? And the way this is parameterized by using a velocity field, so you are going to model this as a people call it a vector. You are going to push at any point in time the particle that is a position x and t by a little vector, and you are going to find one possible set of velocity fields and interpolated measure that actually takes you from the source to the target, and in between that, what you have to do when you see this formulation is you need to have something called a continuity equation, which basically says that if you're giving me a measure that interpolates mu0 to mu and this measure with t is obtained by pushing the mass with velocity, then it makes sense that if I look at around the point x here, the amount of mass that is moving at that point, it has got to be somewhat related to the velocity field and how much mass is moving away from that point and how much mass it is receiving from other points. So this is very simply this continuity equation. So this is just a feasibility constraint. This is just to say something that essentially validates it is basically working to push the mass of that measure. Now, once you do that, as you know, just like in the Moore case, we are going to not be concerned with only whatever. We are going to look for the one that does this properly. So here, the physics, what we like is to minimize the notion of kinetic energy. Kinetic energy is basically how long all of this is, especially when we are going to integrate them in the air. So to summarize, the dynamic formulation of is basically saying among all of those velocities that do the job, the interpolations that do the job, find that which using the source vectors to move from red. Just as the parentheses people call this available foundation, very fast, they are mostly famous for reparameterizing this problem using a new variable, which makes it. Why am I saying this? Well, if you remember your convex optimization, usually if you have a variable and another variable, it's not because you do convex. The x squared and y, not the convex function. But what they did is using this reparameterization, they have something that would be like w squared divided by z, and w squared divided by z is the convex function of the result. The trick was more to introduce a new dimension of thinking. So, in just try to recapitulate the bits or things you see so far. Imagine I have a source dataset, target dataset, giving me this data. What's the emotional relation you could also see it as a gap model or one step generation tries to do is you give me any point x, boom, and give you here. And I'm going to look for that result. Maybe I'm going to parameterize the directions. So the evolution network back in the days, something variable or something a bit more complicated. So this historically was known with integration, but in fact it is actually hard to train integration. So we are always, oscillating between two ends, which is one step generation, which is nice to see, but usually hard to train, and a more dynamic formulation, which is associated with tools of analytical, UODs, etc. And here the idea is I am not going to, from the start, to give you an X, I am not going to give you directly your enhance. I will need to do a bit of test time by integrating a new. And what I'm going to provide the user is no longer a T here that just tells where you left. There's going to be a V velocity field parameterized at T Alex. And so one thing I would like to emphasize is that even if you're doing things optimally, the velocity fields that you get, this is the ground product, the optimal is the variable is time time to change. The only thing that is actually specific to optimal transport in the solution is that what you get is that as you move from the start particle to the end particle, it turns out that the velocity is really the optimal solution. Is always pointing in the same direction. So on one trajectory, on one path, the velocity is different to time. But this is the thing that the velocity is always the same. Again, I'm just trying very hard to show you that these vectors here, no matter where they are, they change. But this is not does not contradict the fact that the optimal transport trajectory is still straight. So out of completeness, which I'm not sure if people like these. So there's yet another formulation that people have used to this is called the Mongeon calculation. So to be brief, I told you earlier, remember that we know that the optimal solution has got to be the greatest of. So in a way, finding this potential is satisfying. It turns out that there is one equation of this potential actually satisfied, and it's the one that you get by just simply re-injecting this push forward constraint. But now, knowing that this is the gradient requirement. So the push forward constraint, if you're using density, is nothing more than the change of variable formula. The change of variable formula that tells you that if you're going, let's say, from U to U by applying C, you're telling me that this actually occurs, the variable is saying. But then you need to have this formula, right? And if you now change T and the determinant of the equivalent of T by actually gradient of S star, well, here we have basically Q of gradient of S star correct. This is going to be the determinant of the hash. And so essentially, this equation is called the most compared equation, and a lot of folks in PDEs, and this is essentially why the things transport like together or primarily we're given the condition, and this is just yet another. But actually, I think the cube is in short now with a lot more. No, I know already what to put behind it. It's clear that it's going to become an example. Anyway, so to recap, and I'm going to see a little bit including your one. You have source to target. You can characterize it as a format. You can also do something funny, which is a bit dynamic and static, which is simply well, if I give you those segments, you might just as well split them, in pieces and make something called the backend interpolation. You have something called the available coordinate formulation, and then you have basically what you get by the all of this is great, but it's very rarely the case, of course, that we'll have access to this stuff. So, in practice, what I haven't told you about is computational tools to solve this small problem. There's a lot of them. Some of them use networks, or use any type of neural networks that we regularize. So there's one family of methods that got a lot of popularity this year. In 2 years, it's so much. So let me try to say a bit what semantic does and actually how it optimizes. So this would be amazing, if we had access to that output. But in practice, it's usually very complicated to get. So what you get instead is just data. And recovering those solutions of data is actually quite fun. So one thing that people did, and is actually very clever, they said, well, let's care too much about finding the optimal output. For now, I am going to find something that's simpler. I am going to create a very simple interpolation between the source and target rhythm, and I will try to regress the velocity field seems to be fitting that simple interpolation. So this method is also known as stochastic interpolation, so much in the future. Denoising, non-denoising, a weird, interesting thing. So here is the gist of it. Yeah, source and target, you have this. What you are going to consider is an interpolation between the two of distribution, which is in a way a lot done than everything that I showed you. I think I was showing you so far, I was carefully trying to be optimal, pushing all of the part of the time away. What we are going to do that is very simple here is, well, I am going to simply come up with a lot. So, okay, practically very simple to explain it. Maybe I have 400 platforms and 400 coupons. I am going to create 16,400 square segments between any of the red points and any of the blue. In other words, I'm going to sample independently an x0, a starting point, x1, and n4. And I am going to create out of this kind of interpolation, which is going to be a probability distribution that immediately will start by collapsing at the source, and then it becomes very, very, very thin. The response that fills up with water, and then reduces again, and then when you reduce it roughly at the target. And what people have done in flow matching is that they now say, well, every time you do this, we sample from the starting point of the source, sample the network of target, sample the time forward to 0, and then just make sure that whatever velocity parameterization you have is going to point in between. At that segment, you know that it's just really taking x0 towards right direction. In ways, like doing the Benamou Fourier formulation, except that you're fixing one of the two variables, which was. And once you fix one of the two variables, it's easier. What we do observe, however, is that fluorescence suffers from a lot of time. So in a way, it's as if you were sampling. So imagine those points here on the lower right, intuitively, you believe they should be going towards the lower right. But when you're doing so much, you're actually not doing that. You're taking any of the points in this part here and still coming with any of the. It's like blind recall. So what you see is, at least on those this is the train model, by the way. What you see in those train models is some wiggling around the origin. So this is something that people actually notice quite early on. And they say, oh, maybe we try to still a little bit of optimal transport in that. But just to recap very briefly, flow matching is essentially taking points in the source, in the targets. It is basically creating this interpolation between them. And now it's going to regress velocity field by making sure it points in the right direction. So the velocity field at point that I sample, at the middle point that I sample here, is basically aligned with the direction That's what people find is, okay, this is just maybe 1 year ago. It's okay, maybe this is really what we could do is take those points that you see or the red and blue, see what we could do by trying to couple them kind of going line. And now I can actually, rather than focusing on putting them, rather than finding this sheet and copying them effectively, try to put some effort in trying to join them to better. So this was tried, and I'm going to be very brief. This was tried in those two articles. One of the things that we found out is that those works surprisingly consider very small sample size, and also kind of set a few recipes to compute to use the optimal product formula. Basically, the choice for this is kind of fixed in being fixed throughout the work. And the end here is, so because I'm running out of time, we're going to be very brief. So the idea of this is essentially, instead of using flow matching to sample all of this blur, what the philosophy behind this approach, at least the geometric methods, to regress the vector fit, not so much of all of that blur, but more on points that okay. So again, I'm running out of time, but essentially what I would just simply say that those works were focusing on the pen, not the size of the batch, which are very small. One of the reasons was that they using the diagram of the so they were computing topics on the set of one. One thing I'd like to say, as the person who has push this on-track tool, is that we are now able to actually optimal talking matrices of trying to eliminate and eliminate how efficient our relation multiple view or multiple nodes. So we are now currently able to take image depth almost entirely and able to sample as many noises the same type of images in couple. So it's one of the things that we've been pushing it. So I will be very brief here, very fast. Essentially, what we see is a lot of results where only focus on one of the plots because the other plots are basically always showing different chemical setup. But we are seeing that if we increase the batch size from some order of magnitude that was used before to very large batch sizes here, which are here, this entire problem 2 million, then we see performance in here, the lower the better for any of the metrics that we have here. And the other part that we were playing with was this idea of gamma, the regularization parameter. And so we see this working quite well even in condition generation of images, such as here in ImageNet. So again, here we play with, I think, the largest point that we have in 1 million ImageNet. Couple 1 million. This requires some analysis. If you go back to this picture of blue, the green bird versus the red point, this requires computing very large couplings and very large case, but it's actually easy. So yeah, that's my point. Thank you very much.